We're going to do one more example. A person is paid once a month for working at a company. Suppose that the person gets paid randomly, according to the table shown, with a random variable m is the amount of the monthly paycheck. Using the standard SDM of 322, the mean is 3,420. These are all in dollars, by the way. Should be an equal here. This distribution has a particular name, and it's called discrete. So what's happening is this person only gets paid once a month. There's a 50% chance that they're going to get paid this amount. There's a 30% chance this amount, 15% chance this amount, and 5% chance the 4,100. It's discrete because it can only take on these four values, and there's nothing in between. So there's 3,124, and can you make 3,125? No. So this is discrete as the opposite of continuous. This is definitely not continuous. Discrete is just the opposite of continuous here. So this table shows the values that are possible and the chance of getting a particular value, an outcome. Okay, that's all this here. So for example, what is the probability that a paycheck in any given month is equal to 3,900? So m is my variable. What's the chance that it's equal to 3,900? Well, I don't have to do anything special. This is, by the way, is a paycheck. A paycheck means single. So this is n equals 1. By the way, this is my parent population. My parent population is just these four numbers. This is again called the whole thing. Sorry, the parent. This numbers here, the parent population. This whole thing is called a distribution. And I don't know if you can remember this far back, but what is a distribution? A distribution is a marriage of contains outcomes and probability of those outcomes. So that's what a distribution is, but here, unlike the uniform we did or the normal, it's easier to see. What's the chance of 3,140? 50%. Okay, so the chance of this outcome being 3,900 is I'd come over here and read the value, 15%. Notice there's nothing here to do. Just read what's on this table. Notice I could not do this here in the other questions that we've done because I just can't read this area to figure out what this is. I need some speculation. Here again, I can't quite read what this area is either. I need to do some calculation to tell me the chance of being less than 2,000. But not here. Here's just telling you what it is. It's outright. So in other words, the areas are already listed here. By the way, notice one more thing. I take 0.5 plus 0.3 plus 0.15 plus 0.05. What do you get? 1. In other words, 100%. Just like when I look at these areas here, the area has to be 100%. That's what this area. What about the area here? The area here has to be 100%. This is continuous. That's why it's showing these curves are continuous. There's no like break. Everything's just like a big continuous line. To be a legitimate distribution, you have to add up to 1. Cannot be less than 1. Can be more than that. What's the probability that a paycheck in any given month is equal to 3,900 or greater? So now we're okay. I want 3,900 this time or greater. And again, notice a paycheck. A paycheck means n equals 1. This is about parent population. Okay. Both questions A and B are about the parent population. $3,900 greater? Well, so if it's 3,900, that's a 50% chance. Or another thing that can happen is it could be 4,100. And what's the chance of that? 5%. But these are two values that are not connected. So overall, is a 50% chance that it could happen, or is a 5% chance? So together, what's the chance that it could be either 3,900 or the other chance is greater than, which is only other option is 4,100. And the answer is 0.2. Right? If somebody asks you just for fun, what if the chance that m is greater than 3,400? And notice 3,400 is near that mean. Well, the only chance that it could be greater than 3,400 if it's 3,560. And the chance of that is 30%. Or it's also greater than 3,400 or equal to it if it's 3,900. That's a different number, and the chance of that one is 15%. And the chance of being 3,400 or greater, well, the other option is that it could be 4,100 and it's 0.05. But again, I need nothing special. All I'm doing is reading these tables. And the chance of that would be 30, 20, 0.5. I know this is a different question that was not part of this, but again, want to make sure we can read this and how it works. All we have to do for a single value, the parent population, is read this table. We don't need anything special. Do I need to know that the mean is 3420? No. Do I need to know the standard deviation is 328? No. Let's get to C. A fellow worker is paid 34.50. Okay. What is the approximate probability that the average paycheck of the other worker after 40 months is greater than 34.50? So I see this fellow worker, he just gets 34.50 a month. This other worker, what other worker? The one that's getting paid using the scheme. So a person, there's a single person that somehow has been roped into this crazy scheme of getting paid randomly, okay, using this table. So sometimes they get this amount, sometimes they get that amount, this amount, and this amount. So this, well, these questions have been about this single person, but there's a fellow worker that just gets flat 34.50. What's the approximate probability that the average paycheck of the other worker, this person that's getting paid randomly after 40 months, is greater than 34.50? So in other words, can this person getting paid randomly outperform this person? The parent population, I'm going to draw this, is discrete. So this is the parent population. Okay, it's just, and what are we doing? We're sampling 40 of these numbers. And the mean of this population happens to be 3420. And the standard deviation happens to be 328. Okay, so now we're sampling 40. Well, the center of this, how are they getting paid? Using a random number. Yeah, that's somehow they're getting paid random. So I'm looking at the question again. They're paid randomly. So I'm assuming that sampling process. By the way, do I want you to be thinking about this? Everything I'm doing? Yes. Because I want you to really understand what's happening. I'm telling you, this is the most important part of this course. But we're going to do this hinges on all of this. This is the basis of a lot of inference. Okay? And the Pfizer vaccine, how good was it? This, what we're doing here is tied to that. We got sampling process is unbiased. So that means that 3,420 is also the mean of the sampling distribution of means. What about the standard deviation? I'm going to do this one here because I want to make sure we don't lose this fact. The standard deviation of the sampling distribution is going to be the population standard deviation divided by the square root of the sample size, which is 40. What about the shape? Well, this is kind of a hairy part. Is 40 big enough? What does this thing look like? 50% is this, 30% is that number, 3,900 is 50%, 5%. So really, I mean, this is rough, but 50% is that number. If I were to create a little chart of this, it would like, here's one number. It's about 400 apart, something like that. And this is another 400 apart. And this is a little less than 400 apart. It's not as far apart. But one goes up to 50%, one goes to 30%, then half of that amount, and then little tiny sliver of that. So it's only four numbers, but it's some kind of right skewed. Is it severe? No, these numbers are not too far apart from each other. And it's somewhat severe, but moderate. But what is this sample of 40? Is that going to be big enough? Well, right now, especially for discrete, I'm not going to expect you to know the difference. But it turns out that 40 is going to be fine. It's going to be close enough. If you were to see the shape, you'll be shocked how normal this thing looks. It's not, by the way. It is discrete. No matter how big we make the sample size, this is only going to be a bunch of discrete shots. There's a gaps everywhere. But after a while, the gaps are so tight that it looks continuous as far as you're concerned. Sometimes the analogy I like to give is that, you know, those bridges that you see in movies that cross a chasm, right? There's just there's a river below, and it's like a wooden bridge with these slats running across. Well, again, if the slats are really tight, woven, then this path looks completely continuous. Now, if the slats get a little further apart, then all of a sudden it doesn't feel continuous. What's happening here is the slats that are making this thing up are so tight that as far as you're concerned, it's just like a one continuous path. There's almost no breaks in it to your, as far as you can see it and tell, but it's not. It's a bunch of slats. So now all we need to do is go through our process, find the z-score. So we'll go over here, find my z-score. What am I after? Forgot already. Is greater than 3450. So if shares 3420, I need to get to the correct side of the mean. That's the most important part of this. And the right direction, greater than 3450. So here's my mean. This obviously is greater than the mean, but I want to continue in a greater than direction. So what I'm after is that. What is this? it will answer my question. So I'm going to get 3450 minus 3420. Again, I'm finding my z-score and divided by 328 divided by the square root of 40. Again, I suggest that when you calculate these, you do it all in one shot. If you were doing this on a calculator that does not show it well, then what I would do is parentheses, close it, divide by symbol, then parentheses again, slash, and then you'll have a square root symbol, no square root, and then 40. Some required to put more parentheses, by the way. Let's say this is the one that shows parentheses. Then you would close it, and then you need to close this one. You do all that, and what do we get here? Again, when you do these calculations, you should use technology. Do not use a table. If you're one of these classes that uses a table, don't do that. And enter as many values here. See, like I go 5 or 6. That's what I'm going to do for mine. So what I'm after now is, here's the formal writing now, probably that my M is greater than 3450. And I can see this is not even one standard deviation. So this is going to be high as a z-score. So we're very close to the mean. And now I'm going to come into GeoGebra and type that in and go greater than. Enter my z, which is 0.5784. And again, I don't think this is going to register that many decimal places anyway, but I want to be safe. And when I do that, I get 0.2815. So there's about 28.15% chance of seeing a paycheck over 40 months beating or equal, 3450, which is this other person, or greater than that. So, he's got a pretty good chance of beating the other person. Notice that another thing to really, like, you would think, well, remember, if it's right at the mean, right? So this is just something else to consider. And this is important for later. It's going to be very important. We know that if it's at the mean, this is 50%. But we're about, 0.57 away. And you would think it would be close to that, but it's not, is it? Just think about that. So here's one standard deviation. We're halfway there. And at halfway, which is about 0.5, it's a little more, it's like a 0.6 really, closer to 0.6. But that movement, all of a sudden, the area is 0.2815, which is, not that close to that. So just keep that this curve is going down pretty fast.